Hi everyone. So this is the video recording of lecture number 4. Unfortunately, I cannot teach in person for this lecture, so I just make this video recording. So it's going to be both lecture number 4 and lecture number 5. So this part is for lecture number 4. So we'll talk about confounding interaction and indicator or dummy variables in regression analysis in this specific lecture. So here's the outline of this lecture. First of all, I will talk about the concept in biostatistics and epidemiology regarding covariance, confounding interaction, or effect modification, and dummy or indicator variables. And then next, I will show models with interactions, and then models with confounding, and then we'll talk about the show specifically from example how the dummy variable and indicator variables will be included in the regression model, especially when there is interaction between these dummy variables and other variables in the regression model. First of all, we'll talk about covariance. So the covariance is also known as extraneous variables or control variables. So they are independent variables that are not of specific scientific interest, but they can impact a relationship between the dependent variable and independent variable in our research question, or we call the question of interest. And the effects can be interaction or confounding. So this depends on either there's interaction or confounding. This covariance can be called confounder or can be called effect modifier. So we'll show this in the next couple of slides. So first of all, confounding is an epidemiology concept. So the confounding exists if the relationship of interest, so usually relationship of interest is the relationship between the outcome and the exposure variable. So exposure is defined as the predictor variable of scientific interest. So you may have a multiple predictor variables in your data set, but you only can have one predictor variable of the main research interest, and this is called exposure. So if the relationship of interest differs when an extraneous variable is ignored or included in the data set, and then the confounding will happen. So this really means with and without the confounding variable, or we call the confounder, the relationship between the exposure and the outcome will change a lot. And then the extraneous variable is referred to as a confounding variable or a confounder. So this page will really show the confounding using graphic display. So the confounding will exist. So if the confounder, or we call the confounding variable, is related to both exposure variable and the outcome variable. So that's the first condition. The second condition is the confounder or confounding variable is not in the causal pathway from the exposure to the outcome. So in this research question, the main relationship or the question of interest is the relationship between exposure and the outcome. So it really is this relationship. And the confounder must be related to both, but not in the causal pathway. So that is to say, it should not be there's another relationship between exposure and the outcome through the variables right here. So if you through this variable, that will be means exposure will impact this variable, and this variable will impact the outcome. So this will call intermediary variable if this is the case. So in order to be a confounder, it must be the confounder variable have impact on the exposure, and also the confounder have impact on the outcome, instead the other way around. So that has to be the two necessary conditions for a confounding variable, to define a confounder. Okay, the next concept is interaction, or in epidemiology called effect modification. So interaction will happen when there's a condition in which the relationship of interest, again, that is the relationship between the outcome and exposure, will differ at a different level of the covariance. And then this covariance will be referred to as effect modifier. So this is really to say, with a different level of this effect modifier, the relationship between exposure and the outcome will change a lot. So there's a huge difference between the relationship stratified by the levels of effect modifier. So interaction focuses on describing the relationship of interest at different values of the covariance. So remember, this is different from the definition of confounding. So confounding is really see with and without adjustment of a covariance, the effect between exposure and the outcome will change significantly. But here, the interaction really means when we do the stratified analysis, we do the same relationship between outcome and exposure, and that will change across the different levels of effect modifiers. So one example is when we assess the relationship between SPB, which is a systolic blood pressure, and age, and we want to see if gender is an effect modifier or not. So then we must determine whether some estimate of the relationship. So for example, the slope of the regression model, and if they vary between male and female. So remember, male and female are the only levels for gender variable. So if the relationship between systolic blood pressure and age vary between male and female, and then we'll say there is a gender and age interaction. So the notation will be gender cross age. So if we mean gender cross age, we really means there is an interaction between gender and age on the outcome, which is the systolic blood pressure. So here we can employ a statistical test to assess the interaction, in addition to the subjective evaluation of meaningfulness. So this is also a big difference between the interaction and the confounding. So there's really no formal statistical test you can use to identify the confounding problem, but there is a formal statistical test for effect modification or for interaction. So interactions usually should be assessed before confounding is assessed. The use of a summary or adjusted estimate that control for confounding is recommended only when there is no meaningful interaction. So that is to say, we always need to evaluate the interaction first, only when there is no interaction, and then we will see if the covariate can be a confounding variable. So in practice, assessment of confounding require a comparison between accrued, also we call an adjusted estimate of an association, and also an adjusted estimate of association. So really means without adjusting for this potential confounders, and then we will see if there's a big change of the relationship between the outcome and the exposure. So if the crude or adjusted estimates are meaningfully different, and then the confounding is present, and then one or more covariates must be included in the data set in order to have a meaningful answer for the scientific question. Then the definition does not require a statistical test, but rather a comparison of estimate from the data. As I said, there's no formal statistical test for a confounding issue. So usually people use a rule of thumb for that, called 10% rule. So 10% rule really means one, there is a change greater than or equal to 10% between the adjusted and the crude estimate. So if the difference is greater than 10%, and we believe the corresponding covariate is a confounder, and also confounding issue exists in the analysis. Finally, we'll give the concept of the indicator or dummy variables. So they're important, especially when we're looking at there's interaction between categorical variables and another variable. And then the dummy variable will be important. So an indicator variable or dummy variable is any variable in a regression analysis that takes on a finite number of values so that different categories of a nominal variable can be identified. And the term dummy reflects the fact that the values taken by such variables, usually values were like 0 and 1, they do not indicate meaningful measurements, but rather than just the category of interest. So it's very similar to the nominal data as I talked about in lecture number 1. So when you have nominal data, the values for this is really a symbol indicating a specific level of that variable. It doesn't really have a numerical meaning for that. So this is similar for dummy variable. The difference, dummy variable only take two possible values, 0 and 1. And then one example is when we have nominal variables such as marital status. So if our marital status have 3 categories, single, married, and divorced. So for example, if we only consider these 3 categories, and then we can make 2 dummy variables. So if we choose a single as a reference group, so one dummy variable is the comparison between married and single, and the other dummy variable is the comparison between divorced and single. So in general, if your categorical variable has the total number of R categories, the total number of dummy variable you need will be R minus 1. So it's always the total number of the categories minus 1 dummy variables will fully take care of all the categories of a nominal variable.